You know, some of the biggest mysteries in science are happening on a scale so small you can't even see them. Take ozone, for instance. We all know it breaks down, but how? What's the secret step-by-step story of its decomposition? Well, today we're going to put on our detective hats and crack the case. So, how in the world do you investigate a mystery you can't see? I mean, you can't exactly dust for fingerprints or interview witnesses in the usual way. You follow the trail of numbers. Every single piece of data you get from an experiment is a clue. It's a breadcrumb leading you to what's really going on behind the scenes. And this, right here, is our case. We have a theory, a proposed recipe for how ozone falls apart. But a theory is just an idea until you can prove it, right? Our job is to dig into the data, find the clues, and see if they back up this story. Let's get started. Okay, so this is the heart of the mystery. On paper, it looks pretty simple. 2 ozone molecules become 3 oxygen molecules. Easy enough. But the real question is how? What are the rules? What controls the speed of this thing? That's the puzzle we're here to solve. So our investigation kicks off with the main suspect, ozone itself. Let's see what happens to the reaction speed when we play around with how much ozone we start with. Time to examine our first batch of evidence. All right, here's our first data drop. On the left, you've got the amount of ozone. On the right, that's how fast the reaction is chugging along. Just looking at it, you can see that when the ozone pressure goes up, the rate goes up too. But the real question is, by how much? That's where the secret is buried. And this is where it gets really interesting. When you look closer, the ozone pressure more than doubles, right? It goes from about 8 to almost 18. But look at the rate. Whoa! It doesn't just double, it jumps by a factor of 5. So when you roughly double the main ingredient, the speed basically squares. And boom, that right there is a huge piece of the puzzle. In chemistry, we call this a second-order relationship. The effect isn't just 1-to-1, it's exponential. Doubling the ozone squares its impact on the speed. This is a massive clue. Let's file that away. Okay, so we've interrogated our main reactant, but any good detective knows you've got to check out everyone involved. So what's the deal with the product? Oxygen. I mean, you wouldn't expect it to do much, would you? It's what's being made. Well, let's see. All right, next set of data. This time, we're doubling the amount of oxygen in the mix, from 200 to 400. Now, look at the rate on the right. What's happening? Wait a second. It's going down. That's just weird. This is a massive twist in our case. Think about what just happened. We added more of the stuff the reaction is supposed to be making, and the whole process slowed way down. Doubling the oxygen literally chopped the reaction speed in half. At first glance, that makes absolutely no sense, but it's a critical clue. What this tells us is that oxygen isn't just a harmless byproduct, just sitting there. No, it's actively getting in the way. It's an inhibitor. It's like finding out that someone in the room is secretly trying to sabotage the whole process. This completely changes how we look at this thing. So we've looked at the ingredients and the final product. But what about the kitchen itself, the environment? Let's see what happens when we crank up the heat. I mean, we all kind of know this intuitively, right? Heating things up makes reactions go faster. That's the whole principle behind cooking. But why? What is heat actually doing to all those tiny molecules? The answer is something called activation energy. The best way to think about it is like every reaction has to get over an energy hill before it can happen. Heat is like a turbo boost. It gives more of the molecules the oomph they need to make it over the top of that hill. And by running experiments at different temperatures, chemists can actually calculate exactly how high this energy hill is for our ozone reaction. Okay, let's recap. We've got our clues. We know ozone has a squared effect. We know oxygen surprisingly gets in the way. And we know there's an energy hill to climb. Now, it's time to bring our suspect back in, that proposed mechanism, and see if its story matches the evidence. This is the final showdown. So here's the theory again. It says, this whole thing isn't just one big step. First, an ozone molecule actually splits apart. This creates this super unstable temporary particle, a single oxygen atom. We call it an intermediate. It's like a ghost particle. It's there for a split second, and then it instantly collides with another ozone molecule to finish the job. That's the proposed. So how do we turn this two-step story into one prediction we can actually test? Well, chemists have this brilliant trick up their sleeve called the steady state assumption. It basically says that that ghost particle, the atomic oxygen, is like a hot potato. It gets created and used up so fast that its concentration basically stays at zero. It's a clever assumption that lets us mash the two steps together into one master equation. And this is it. This is the master equation, the rate law that our two-step theory predicts. Now, I know it looks a little intimidating, but don't worry about the math. Just think of this as the mathematical fingerprint of our suspect. So, for the moment of truth, does this fingerprint match the clues we found at the crime scene? Let's run the comparison. See how our theory puts ozone squared up top in the numerator? That predicts the rate should get faster with the square of the ozone. And what did clue number 1 tell us? Exactly that. Check. Now look at oxygen. It's down in the denominator. That predicts that as oxygen goes up, the overall rate should go down. And what did our crazy clue number 2 show us? That oxygen gets in the way? It's another perfect match. Bingo! The theory predicted everything. It explained the weird squared effect of ozone, and it totally explained the bizarre twist where oxygen slows the whole thing down. The story holds up. The evidence confirms the theory. Case closed. And that's really the big takeaway here. We took a reaction that looks simple on the surface. We gathered clues from data that were confusing and even seemed wrong at first. And then we showed how a theoretical model could explain every single weird detail perfectly. This is how we pull back the curtain and see the secret, step-by-step story of how our world works at the molecular level. And that really gets you thinking, doesn't it? This detective method, following the data to uncover a hidden mechanism, it's not just for ozone. It's how we figure out how medicines work, how catalysts clean our air, really how life itself functions. So what other incredible, invisible stories are unfolding all around us, just waiting, leaving a trail of clues for us to find?